Hey guys, Alexander here, and welcome to another video in the Probability and Statistics series. In this video, I will be introducing to you the gamma distribution and some of its properties, its probability density function, its expected value, variance, and moment generating function. And I will conclude this video with a few remarks and some example questions that you might encounter in your pursuit of studies of statistics. So the gamma distribution. The gamma distribution is used to model the random time elapsing until a specific number of events have occurred. Think of it as counting a group of independently identically distributed exponential random variables. Now, we've covered exponential random variables in a previous video of mine. I will put the link in the description for you to, if you cannot recall. But the gamma distribution is, in a sense, think of it as I'm counting a certain number of independent, identically distributed exponential random variables. And that certain number of them refers to this parameter over here, alpha. Alpha is the number of these IID exponential random variables that we are counting, alpha of them. Alpha is the shape parameter, and lambda is the same as the lambda from the exponential distribution, that is the rate parameter. Shape and rate, and both of them have to be greater than 0. So if x is a positive random variable with a probability density function of lambda e to the negative lambda x times lambda x to the power of alpha minus 1 over alpha minus 1 factorial for the support of x being greater than 0 and 0 otherwise, then x is said to follow the gamma distribution with the rate parameter of lambda and the shape parameter of alpha. I want to point out something very important. The exponential distribution is a special case of the gamma distribution, and note how I have written this probability density function. This part looks oddly familiar. This is the PDF of an exponentially distributed random variable, lambda e to the negative lambda x. What makes it a gamma is the part here on the right hand side. Lambda times x to the power of alpha minus 1 over alpha minus 1 factorial. Now, I told you that an exponential distribution is a special case of the gamma. Well, how do we see that? If you set the shape parameter alpha to be equal to 1, if we say it's a gamma with 1 lambda, and you plug that 1 into this alpha over here, this exponent then becomes 0, so this becomes 1. This becomes 1 minus 1 factorial, which is 0 factorial, which is defined to be 1. And then we are simply left with a PDF of an exponential distribution. That's how simple it is. But it is important that you see and realize that the exponential distribution is linked to the gamma distribution, and you need to see how they are linked, because this will become very critical for the following videos that will cover how you derive the expected value, how you derive the variance, how you derive the moment generating function. Note that gamma of alpha is equal to alpha minus 1 factorial, and that gamma of 1 is defined to be 1. The gamma distribution has an expected value of alpha over lambda. It has a variance of alpha over lambda squared, and its moment generating function 5x of t is given by lambda over lambda minus t to the power of alpha for t less than alpha. And if you recall from the exponential distribution, this is simply lambda over lambda minus t. This is this part inside the brackets of the gamma distribution. And this alpha is simply the number of IID exponential random variables that we are counting together, that we are adding up to make a gamma. So you can think of a gamma as the sum of alpha identically independent identically distributed exponential random variables with the rate parameter of lambda. Now let's look at some example questions that you might see. Suppose that we are the managers of a canteen, a restaurant, and that each customer arrives independently and identically on average every 5 minutes. So each customer has an arrival time that is distributed exponentially consecutively with a mean of 5. That means that 1 over lambda is 5. Thus, lambda is equal to 1 over 5 or 0.2. So we wish to study the amount of time for 10 customer arrivals. What is the distribution followed by this process? Then, if we know that each of these 10 customers is individually and identically distributed with a rate parameter of 0.2, then the sum of these 10 customers, their arrival times is distributed as gamma with a shape parameter of 10 and a rate parameter of 0.2. What is the probability that the manager would have to wait between 4 and 6 minutes for the 10 customers to arrive? Now we see that each customer takes on average 5 minutes to arrive. So for all 10 of them to arrive between 4 and 6 minutes in such a narrow interval, we expect it to have a very low probability. So how do we go about this calculation? Well, we use the fact that the probability that x is less than 6 and greater than 4 is simply the definite integral from 4 to 6 of the probability density function of the gamma distribution. So we have lambda e to the negative lambda x times lambda x to the power alpha, which is 10 minus 1 over alpha minus 1 factorial dx. And if you evaluate this using statistical software or programming languages or your calculator, you will find that the answer should be this. And this is a brief introduction to the gamma distribution. I hope it has made it accessible and simple enough for you to have a taste of what it's going to be like, because in the following videos we will be going through the process of deriving the expected value, deriving the variance, and deriving the moment generating function. And you might be saying, oh my goodness, I don't want to do all of that integration. But I can guarantee you we won't be doing a single bit of integration in either of those 3 scenarios. Thank you for watching. I hope you've enjoyed this video. Book Commander out.